Welcome to our next lesson on second-order systems and mechanical applications. So for the mechanical system, we will assume that three masses are connected to each other and to two walls by four springs, such as in the picture here in the upper right-hand corner, where the masses slide without friction, and that each spring obeys Hooke's law, where the force F is equal to negative K times X. Applying Newton's law to the three masses then will yield us our system of ordinary differential equations. M sub 1 times X sub 1 double prime is equal to negative K sub 1 times X sub 1 plus K sub 2 times X sub 2 minus X sub 1. M sub 2 times X sub 2 double prime is equal to negative K sub 2 times X sub 2 minus X sub 1 plus K sub 3 times X sub 3 minus X sub 2. And finally, M sub 3 times X sub 3 double prime is equal to negative K sub 3 times X sub 3 minus X sub 2 minus K sub 4 times X sub 3. This gives us the displacement vector X, just to be those values X sub 1 through X sub 3. The matrix M, each mass is on that main diagonal from M sub 1 through M sub 3, and everything else is zeros. The stiffness matrix, K, this takes for values negative of K sub 1 plus K sub 2, K sub 2, 0, K sub 2, negative of K sub 2 plus K sub 3, K sub 3, 0, K sub 3, and negative of the quantity K sub 3 plus K sub 4. And this system becomes M times X double prime is equal to K times X. So the homogeneous second-order system, since M is non-singular, multiplication of its inverse yields the homogeneous second-order differential system. X double prime is equal to A times X, with A is equal to the inverse of our matrix M times that matrix K. So theorem 1, second-order homogeneous linear systems. If the n by n matrix A has distinct negative eigenvalues, negative omega sub 1 squared down through negative omega sub n squared, with associated real eigenvectors v sub 1 through v sub n, then a general solution of X double prime is equal to AX is given by taking X of t is equal to the sum from I is 1 to n of A sub I times the cosine of omega sub I t plus B sub I times the sine of omega sub I t, all of that times V sub I, with the A sub i's and B sub i's as arbitrary constants. In the special case of a non-repeated zero eigenvalue, lambda sub 0, with associated eigenvector, we could write this simply as X sub 0 of t is equal to A sub 0 plus B sub 0 times t, the whole quantity times V sub 0. So example, I have considered the mass and spring system with n is equal to 2 shown above. Because there is no third spring connected to a right-hand wall, K sub 3 would be equal to 0. If M sub 1 is equal to 2, M sub 2 is 1, K sub 1 is 100, K sub 2 is 50. We want that general solution. So this system being M times X double prime is equal to K times X. So our matrix M, based on the two masses that we have, 2, 0, 0, 1, times X double prime is equal to, so using those values of K, this is negative 150, 50, 50, and negative 50 times X. Okay, so for us to actually go around and solving this, we would need to take the inverse of m from both sides here. Taking the inverse of m. So doing so will give us our new system. X double prime is equal to ax, and A being that inverse of a matrix M times the matrix K would give us negative 75, 25, 50, and negative 50. And that is due to the fact that the inverse matrix of M, that was a half 0, 0, 1. And the matrix K was this negative 150, 50, 50, and negative 50. So multiplying those gave that matrix A. So the characteristic equation. Characteristic equation. Okay, so taking that from this matrix A here then, when we subtract the lambdas, this will be the determinant of negative 75 minus lambda, 25, 50, and negative 50 minus lambda. So that is going to be negative 75 minus lambda times negative 50 minus lambda. Then that'll be minus 25 times 50, or minus 2,500. Excuse me, that part does not 2,500. So the 50 times 25, that would make, once this decides to erase on me, that is going to give us a value for 25 times 50, which will be 1,250. And we're subtracting that. And that's going to be equal to 0. So, multiplying, combining like terms, all that, this makes lambda squared plus 125 lambda plus 2,500 this time is equal to 0. So we can factor that. This factors to be lambda plus 25 times lambda plus 100 is equal to 0. So we get two eigenvalues. Lambda sub 1 is negative 25, and lambda sub 2 is negative 100. So, by the theorem 1 that we were just looking at, the circular frequencies that we have this would be omega sub 1 would be a value of 5, and omega sub 2 is a value of 10, since those will be squared to get the two lambdas. So case 1, lambda sub 1 is equal to negative 25. That makes our solution now A plus 25i times v is equal to 0. So that becomes negative 50, 25, 50, negative 25 times AB is equal to 0, 0. So in doing so, right, both of these obtain the same type of thing, where we would have B is equal to 2A. So our eigenvector V sub 1 this would be equal to A and 2A. So factoring that out, that A, we get our eigenvector to be 1 and 2. Or that lambda being equal to negative 25. For case 2, lambda sub 2 is equal to negative 100. So A plus 100i times V is equal to 0. And that becomes 25, 25, and 50, 50. Again, times AB is equal to 0, 0. So here, B would be equal to negative A. So another eigenvector would be V sub 2 is equal to, this would be A negative A. So A times the eigenvector 1, negative 1. So as a combination, x of t, this will be equal to A sub 1 times the cosine of 5t plus B sub 1 times the sine of 5t times V sub 1, so in this case, 1, 2, plus A sub 2 times the cosine of 10t plus B sub 2 times the sine of 10t times the eigenvector V sub 2, so 1, negative 1. So for the forced oscillations in resonance, the ith mass in the mass and spring system is subjected to an external force, in addition to the forces exerted by the springs attached to it. So now we have a non-homogeneous equation, m times x double prime is equal to k times x plus f, with f being the external force vector f sub 1 through f sub n. And taking the inverse of m now leads to x double prime is equal to ax plus f, where the lowercase f is the external force vector per unit mass. And this would include periodic external force f of t is equal to f sub 0 times the cosine of omega t. And the periodic particular solution, x sub p of t, is equal to c times the cosine of omega t. The linear system would become a plus omega squared times I times c is equal to negative f sub 0. And so, because of that, here's an example. Example number 2, we want to suppose the second mass in example 1 is subjected to an external periodic force 50 times the cosine of omega t. So with m sub 1 being 2, m sub 2 being 1, k sub 1 being 100, k sub 2 being 50, and f sub 0 to be 50. We want the solution. And you could see we have a picture here in the upper right. detailing those two springs, the two masses, and the force being applied to it. So what we want here is x double prime is equal to ax plus f. So x double prime would be equal to negative 75, 25, 50, and negative 50. That came from example number 1 that we did a few minutes ago. Times x is equal to, plus so be plus 0.50 times cosine of omega t. All right, so if we were to let x to be c times the cosine of omega t, then we would have omega squared minus 75, 25, 50, and omega squared minus 50. Times c is equal to 0 and negative 50. So, the value for c sub 1, this will be 1,250 divided by omega squared minus 25 times omega squared minus 100. And c sub 2 makes negative, this will be 50 times omega squared minus 75 divided by omega squared minus 25 times omega squared minus 100. So, based on that, so the external squared frequency is going to be omega squared is equal to 50. So because of that, c sub 1 will just give us a nice number of negative 1, and c sub 2 also gives negative 1. So the forced periodic oscillations oscillations would be x sub 1 of t is equal to the negative cosine of omega t, and x sub 2 of t is negative cosine of omega t. So this oscillates in synchrony. Oscillates in synchrony with equal amplitude, in the same direction. So that was if omega squared is equal to 50. Let's say now if omega squared is equal to 125, excuse me. Then C sub 1 is 1/2, and C sub 2 is -1. So the forced periodic oscillations would be x sub 1 of t is equal to 1/2 times the cosine of omega t, and x sub 2 of t is negative cosine of omega t. And then this one will oscillate in synchrony in opposite directions. And the amplitude of m sub 2 motion is twice that of m sub 1. Thank you for watching. Let me know if you have any questions or concerns. Thank you.